I understand that you served on the team of NASA's Mars exploitation or exploration probably
Yeah, not
probably
exploitation.
exploration rover MER mission. And given that this mission ended about 5 years ago, maybe before we get into your role, could you just lay out the basics of what the mission consisted in, the non-exploitative explorative mission?
Yeah, this was the first of a series of rover missions, which there are two others still operating today. Um, it was not to find evidence of life, either ancient or modern, on Mars, but to understand Martian environments, past and present. And in essence, the rovers, their names were Opportunity and Spirit and Opportunity, which might ring bells with some of your viewers. And in essence, these rovers were doing much the kind of work that I've done on Earth in the past. They look at ancient Martian rocks. There were chemical instruments that could tell us something about the chemistry and mineralogy of these rocks. There's even a hand lens, so you could see very fine scale textural features of the rocks, a series of cameras. And so, really, for about 13 years, um, Opportunity in particular was able to traverse among outcrops of ancient rocks and tell us something about the history. It's our first real ability to try and reconstruct the history of another planet, and it was really a privilege to be part of that team.
Yeah, and what was the part you played? What was your role in the project?
Well, too, I think one of the reasons why I was asked to join the team was simply that I did have this experience of you know trying to understand environmental history from ancient rock. So, along with all the other team members, I was involved in interpreting what the rovers told us on a daily basis. Also, I was one of several people over the course of the mission who was responsible for what's called long-term planning. And to think about that, uh, you have to make both tactical and strategic decisions. Tactical decision is what should we do tomorrow? Strategic decision is what are the big questions we can ask of this outcrop, and how do we go about answering them? And so I was one of the long-term planning or uh, strategic leads as well. But it was very much the nice thing about the mission was that everyone's voice was important. We all listened to each other. We learned how to integrate the results from different types of observations. And because of that, we were able to learn something about what Mars was like as a young
Hmm.
planet.
But you made it clear at the outset of your response that this project was not so much or not at all about astrobiology, but was really about geology. And this notwithstanding, did you determine whether or not the soil or terrain more generally was conducive to life? And I suppose that in asking this, there are two questions. One, do you think it is possible that there might have been life, at least as we know life, on Earth in Mars past? And in a more forward-looking sense, could we, in theory, transport any of Earth's own microbes there and expect them to thrive?
There's a number of questions in there. Let me try and unpack it. Um, yes, the mission had no instruments that would be specifically designed to detect or characterize life. The idea was to say, what were environments like? Because if the environment is not conducive to life, then the story is over. Now, some of the more recent missions have more sophisticated instrumentation that can help, although I'm not sure they can or have uh, reported anything that is definitive evidence of life past or presence on Mars. But what we were trying to do was to understand the planetary history, which then provides a framework for thinking about some possible history of life. And before we ever landed in Meridiani Planum for Opportunity, people had known from remotely sensed observations by satellites that Mars was once wetter than it is now. There's ancient river systems, there are ancient deltas, uh, lots of things that tell us that in the past there was liquid water on Mars. Now, the rocks that we looked at on Opportunity, where there are signs of water, but as I like to say, it's signs of water waving goodbye. So we have certain mineralogies and features that could only have formed in the presence of water, but they would not persist in or in the I'm sorry, they would persist only in the absence of water. So certain types of minerals form when they need water to form, but if you keep water around, they will transform into other minerals. And so what we found, and my former postdoc Nick Tosca, who's now a professor at the University of Cambridge, were able to determine that in the places we were looking at, Mars went from at one moment being wet environments, but as they dried out, you basically left the habitable zone of life, and there's very little evidence that they ever got wet again. So, and I think other places have seen this, that there's evidence that water could have been present for tens of thousands of years in some places. There were lakes, there were deltas, that sort of thing. But you spread that out over a period of 1 billion years, and it could have been dry much of the time. And some people, myself included, but not everyone, is of the opinion that while Mars was at some times relatively wet, that early Mars was episodically wet and dry. And so it's the implications for life are very different if you think that Mars was wet for 1 billion years versus Mars was wet for 100,000 years, then dry for 1 million, then wet for 10,000, then dry for another 2 million. And we're still struggling to understand the details of that. But I think it's at least reasonable to think that even in the earlier history of Mars, which clearly has evidence for running and standing water, that those might not have been continuously present. So at this point, we don't know whether life ever began on Mars. If it did, it didn't persist, at least at the planetary surface. I think if you just drop random bacteria onto Mars, which we've probably done through some of the rovers, they would not be likely to persevere because there is so little water, so little access to nutrients. So I think if you want to have life on Mars, you got to get Matt Damon to go up there and grow potatoes in some human-built structure. I'm skeptical of the idea that Mars is currently not only an inhabited planet, but at the surface at least, a habitable planet.
Would you add the caveat that you're skeptical that at the surface it is a habitable planet, but only if Martian life resembles Earth life in the sense that it requires water, because presumably there are myriad other possibilities that life could take that where water isn't so vital?
Well, that's an interesting question, and a lot of people have thought about it. I think we, in some ways, instinctively think about life as we know it, which is equivalent to life on Earth. As I used to say to my students, that if you don't make that assumption, games without rules have many possible outcomes, and so you can just speculate all over the place. Now, having said that, water is a very unusual substance in many ways, and it's a particularly biofriendly substance. And so while there might be places in other types of planets where other molecules could play the role that water does, on most rocky planets, including Mars, I think water is probably the only game in town. And there are certain characteristics, physical characteristics of water that uh, are likely to affect life of any sort. You know, on this planet, once you get to a salinity above a certain point, life doesn't exist. I mean, it's the reason that our ancestors used to salt meat or add sugar to preserve fruits, and that lowers the so-called water activity. That is the percentage of water molecules that at any given moment can participate in the chemistry of water. And I think likely the limits imposed by water activity, the limits imposed by something called chaotropy, which some ions are actually destructive of polymers like peptides or nucleic acids. So I suspect that while, you know, we don't know that life on Earth is the only type of life that can exist, my guess is that wherever we find life, it'll be based on carbon. There's a fairly large chance it will be environmentally based on water. Um, and that's about what you can say.
That's a very
You
helpful
know,
answer. Yeah,
okay.
that's great. I've spoken to one other astrobiologist. I don't know if you want to consider yourself an astrobiologist, but I've spoken to one other, I'll call you one. I've spoken to one other astrobiologist on the show, and her name's Clara Sousa Silva. I think she was at Harvard for a while. She's at Bard now, but she was part of this project, I believe, led by Sarah Seeger of MIT, that you might recall this a few years ago. They believed they'd found a signature of life on Venus, particularly in the clouds of Venus. But the way that Clara works is by looking at the spectra of exoplanets to determine the contents of their atmospheres. And based on these contents, she's then able to deduce whether there's a possibility of life there, because some atmospheres, particularly atmospheres in her case that are high in a compound called phosphine, are highly unlikely without life because they require a particularly complex chemistry that you are unlikely to find in geologic features. But as you know, as we've already talked about, life has very much created the atmosphere that we now inhabit on Earth, which is why finding phosphine would be so important. But is there, in the same way that I sort of simplistically laid out how her astrophysics and chemistry work functions in an astrobiological context, is there a somewhat is there a simple way of describing the way that your more terrestrially focused work would become applicable to astrobiology in the event of a mission that were explicitly devoted to astrobiology? So, for instance, what sorts of things on a rover like Spirit and Opportunity would you want it to have so that it would be optimized to search for life when you're getting data sent back to you?
Yeah, there's a series of good questions in there.
I like to
Um,
hear that.
I think the
Thank you.
first thing I think the first thing to say is that the way you can do astrobiology depends on what you're looking at. The kind of work that I've been privileged to do is something we can do in our own solar system because you can go there and at least send a rover, if not a human being. And I think over the next 20 years, we're going to see missions to moons of Jupiter and Saturn that are candidates for biological planets. Um, the kind of work you were talking about on looking at planetary atmospheres, that's what we can do to looking at extrasolar planets, at least within our own cosmic vicinity, you know, a couple of light years. And people like Sarah Seeger and others have made real progress in our ability to actually understand the chemical composition of other atmospheres, and that's all exciting work. One of the questions, which provokes a lot of debate, is whether there is any atmospheric signature that is uniquely and diagnostically biological. And I have to tell an anecdote here because years ago, I was having dinner with a man named Dave Stevenson, who's a Caltech professor, one of the great planetary scientists of our time. And we were just talking about this subject. And, I sort of parroted what everybody else was saying at the time and still are largely that, if you found an atmosphere that simultaneously had oxygen and methane, since those two don't coexist at equilibrium, that would be evidence of life. And Dave just smiled and he says, I'm willing to bet you that when that observation is made, within a year, there will be at least 6 published papers showing models of how that can happen without invoking life. And I think that's certainly what happened on a more rapid time scale with the phosphine observation. And so I think it remains an interesting question that deserves careful thought about, what can you say definitively about habitability or inhabitation based on a planetary atmosphere. And then, if you think about it, for most of the universe, the only way we'll ever know if there's life out there is if they tell us. That's really where that comes in. So I think we're going to see more bio-focused instrumentation on different missions. I know there's a lot of people who would like to go to Enceladus, moon of Saturn, that certainly has geysers. And those geysers are known to have organic molecules in them. And so you can take instruments that would gather and analyze the composition of those geyser effluvia. Going back to Mars, there are more sophisticated ways of examining organic matter. My own feeling is that what we would love to do, and I know it's technologically challenging, would be to actually drill relatively deep holes into the Mars subsurface, where not only is there some possibility that there is a subsurface biota, but more importantly, unlike surficial materials, things at depth might have had less alteration due to interactions with the surface environment. So there's a lot of things that will happen. It is, putting together a mission to any of these places is really challenging. And I admire the people who do these missions and carry them out. But my guess is that over the next 20 years, we will see both increasingly sophisticated and biologically oriented missions within our own solar system and an increasingly sophisticated efforts to understand planets beyond our solar system based on chemical signatures that we can see by remote sensing.